afternoon, everyone, and welcome to today's plenary session of the Virtual Math Fest. My name is Diganta, and I am from IISc Pune. It is my great pleasure to chair this session and introduce the speaker, Professor Gautam Bharali. Professor Bharali is from Indian Institute of Science, Bangalore. He works in complex analysis, more specifically several complex variables. Which is in simple words means that the study of holomorphic functions defined on domains in higher dimensional complex Euclidean spaces. Professor Bharali completed his undergraduate studies from IIT Kanpur and received PhD from the University of Wisconsin-Madison. He is a very sound mathematician and eminent teacher. Today, he is going to tell us about behavior of proper holomorphic maps in several complex variables. Gautam, we are very proud to have you here, and I now request you to deliver the talk.
Thank you, Diganta. Thanks for the introduction. A quick question, am I audible?
Yes.
Okay, excellent. So I'd like to begin by thanking the organizers for giving me an opportunity to speak at this virtual math fest. And as a matter of fact, I should congratulate them. This is probably the first virtual conference in India at this scale, virtual conference for a general math audience. So congratulations for pulling this off successfully at this scale, at this large scale, right? So that said, let's proceed. Yes, here we go. Right. I begin with the aim of this talk right up on the screen. But before I dive into the aim, I'd actually like to say that this talk is really an excuse to say a few words about how complex analysis in two or more variables is a completely different discipline from complex analysis in one variable. This is the flavor of complex analysis that a large number of you in the audience are familiar with. It is also an excuse to talk about maybe just one or two results in complex analysis in one variable that many people know, but whose proofs may not be equally well known. And also to present an aspect in this rather vast discipline called several complex variables, where the techniques involved, the techniques for proving results involve both analysis and geometry, right? So that said, you can see up on your screens the aim of this talk, which is to survey various instances of the following phenomenon. Let D1 and D2 be two bounded domains at Cn. And I'm going to insist that unless otherwise mentioned for the purposes of this talk, the dimension n is greater than or equal to 2. So you're given these two bounded domains and their boundaries are reasonably nice. And the interpretation of nice will depend on the scenario. So the phenomenon is that with reasonably nice boundary geometry, any proper holomorphic mapping from D1 to D2 is a biholomorphism. So the first thing that will occur to me, all right, what are the meanings of all of these words that I just encountered, right? So let's get on with that. Let's first start with this word proper. This is probably the most familiar definition. Given a pair of topological spaces, X and Y, a continuous map from X to Y is called proper if every compact in the pre-image of every compact in Y is also compact, right? So this is a definition that is familiar to many of you. And now let's define holomorphic. So holomorphic is synonymous with the word complex analytic. So complex analytic, holomorphic, these are synonyms. But what I want to define is this notion in several variables. As I read through this, you will notice the definition is as it should be. The definition is what you would expect from one variable, which is given an open set in Cn, called the set D, a function on D is said to be holomorphic if given any point A. F can be expressed as a power series in Z1 minus A1, Z2 minus A2, dot, 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 Zn minus An, at every point in a specific set in some polydisk. This is the Cartesian product, the disk dA1, R1, Cartesian product dA2, R2, dot, 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 dAn, Rn. So this is a certain, it's a Cartesian product of disks centered at the point A. And I should say something about the convergence. This power series is required to converge absolutely at each point, right? So nothing different. This is exactly as you would expect from the definition you all know in one variable, which is locally, your function f is expressed as an absolutely convergent power series. I would like to note that in giving this definition, I've also defined what we mean by the term polydisk. A polydisk is simply a Cartesian product of disks, planar disks. Okay, next. So we'd like to know when a vector valued map. So what I defined previously was a complex valued function. A vector valued map, capital F, from the same open set D, this time into Cm, is holomorphic if every coordinate function is holomorphic. And lastly, there was in the first slide this word biholomorphism. So let's define that. A holomorphic map from a domain D1 to a domain D2 is a biholomorphism if F, this map capital F, is bijective, and so the subtheoretic inverse, this is now a map from D2 to D1, is also holomorphic. So in other words, a biholomorphism is for those of you who are familiar with this language, it is an isomorphism for this category, which is the category of domains and holomorphic mappings between them. All right, so all of these definitions, they appear to be obvious generalizations of familiar one variable definitions. But the point I want to make is that I said right at the beginning that complex analysis in two or more variables is a fundamentally different discipline from complex analysis in one variable. Of course, they do have overlaps, but many results in one dimension do not extend to higher dimensions. And then there are results in the higher dimensional setting that have no analogs in one variable. All right, so let's look at an example. Whenever you meet someone who talks to you, who starts talking to you about several complex variables, chances are that this result that I just flashed is the result that they will quote as illustrating how several complex variables differs from complex analysis in one variable. So let's read this result out. And please note, this result is strictly for the case where the dimension is greater than or equal to 2. So for n greater than or equal to 2, the round ball, the open round ball in Cn, I'm going to, in this talk, denote this ball by boldface b to the power n. The open round ball in Cn is not biholomorphic to the unit polydisk in Cn. The n equal to 2 case was known a long time ago, and this was a result by Poincaré. And note how this result, number one, it has no analog in one variable for the simple reason that the Euclidean ball and the polydisk in one dimension are just one and the same thing. But I also want to point out that the result that I have stated illustrates one of the first divergences from what you would expect in the complex plane. Namely, the unit polydisk and the round ball are both simply connected open sets. In fact, they are better than simply connected. They are even simpler. They're contractible open sets. Now, in the plane, any simply connected open set that is not the complex plane itself, you all know, is biholomorphic to the unit disk. That is the Riemann mapping theorem. So what this theorem here is saying is that there is no Riemann mapping theorem in higher dimensions. I am going to give a proof of this theorem, but the proof I'm going to give is not, in fact, it is in the style of the proof given for n equal to 2 in Poincaré. But the path I'm going to take is one where the proof is actually going to drop out indirectly from the theme that I announced on the first slide. So moving on further, I want to stay on this topic of one dimension versus higher dimensions for a little bit more. Consider the unit ball in C. So I'm kind of deliberately calling the familiar disk that a lot of you in the audience are familiar with. I'm deliberately calling it the ball, the unit ball in the plane. And I want to describe all proper holomorphic self-maps of the unit ball in C. They are, up to a rotation, a product of a bunch of positive integer powers of these maps that you are all familiar with. These are disk automorphisms. So these are called Blaschke products. And I actually want to give some hints as to how you prove this statement. I leave it as an exercise for you to fill in the details. So first of all, remember, we are trying to describe all proper holomorphic self-maps. So the singleton 0 is a compact set. So its inverse image under F is a compact set. But it is also, remember, this is a property of holomorphic functions. It also has to be a discrete set. So this inverse image is a finite set called the set A1 through AN. These are distinct points. Now what you do is you compose F on the left by a disk automorphism that maps the origin to the first of these points up here, to A1, which gives you an auxiliary map. I'm going to call it F tilde sub 1, which is still a self-map of the proper self-map of the open unit disk, but now fixes the origin. Also called M1 the order of the 0 at the origin of F1 tilde. So I want to point out that this M1 over here is one of these M's up here. All right, so this is the first move. This is the first move in the proof. The second move is you apply the core of the argument for proving the familiar Schwarz lemma. Remember, if you have a self-map of the open unit disk which fixes the origin, you can factor out Z. But you can actually do better. Remember, you can actually factor out a power which is given by this order over here. So this is the second move. And now what you do is you just repeat these last two moves finitely many times. And that's the sketch of the proof, which will give you this description up here. So, proper holomorphic maps of the unit ball in C are very much many-to-one maps, right? See this description up here. In general, these are many-to-one maps. However, this is in stark contrast with a result by Henri Cartan. So there are actually two Cartans in this talk. So there is Henri Cartan, whose name is familiar to you, and then there is the elder Cartan, who I will also be talking about, Élie Cartan, later in this talk. So a very young Henri Cartan was the first to prove this rather interesting result, that when you look at the unit ball, not in C this time, but in C2, then any proper holomorphic self-map is forced to be a biholomorphism. Remember, this is the phenomenon that I had advertised in the first slide. All right, so this is that result. Very different story in 2 dimensions from the story in 1 dimension. All right, before we get into Cartan's theorem, let's probably look at a result which is somewhat within the framework of Blaschke products. Let's do that also. Okay, so for completeness sake, I want to mention a result which is an important result in this area. This is by Remmert and Stein. So for the analysts in the audience who would have heard of Elias Stein, may probably have read his books. This is Stein. This is an older mathematician, Carl Stein. So the Remmert-Stein theorem is about proper holomorphic maps of products. So consider a bunch of bounded domains, dj and omega j, sitting in complex Euclidean space. I'm calling this Cnj, j running from 1 through k. If you feel muddled up by the subscripts, just assume j to be 2 over here, okay? So what I want is a non-trivial Cartesian product. I also want a condition on the boundary geometry. And this is a boundary geometry for these target guys, for these omega j's. Assume that the boundary of omega j does not contain any, well, I was about to say, does not contain any analytic varieties of positive dimension. What I simply mean is that the boundary is such that that it does not contain merely germs of non-trivial analytic varieties, okay? So planar domains would satisfy this condition up here. Now consider a proper holomorphic map from the Cartesian product of the dj's to the Cartesian product of the omega j's, all right? Then I'm now going to give you a complete description of such a proper holomorphic map. There exists a permutation on k letters, so k is this parameter up here, and there are holomorphic maps g sub j on the Cartesian factor d sub sigma j, where g sub j maps d sub sigma j to omega sub j. The dimensions n sub j and n sub sigma j line up, and this map g sub j is proper. Okay, so these are your protagonists. And the proper holomorphic map fz has this particular form. It is a vector of these mappings g sub 1 through g sub k, which, as you can see, do not depend entirely on the vector z, but depend on a sublist of these variables. So that's the structure, general structure of a proper holomorphic map between Cartesian products. And then probably more illustrative than this theorem is this example that consider the unit polydisk. Any proper holomorphic self-map of the unit polydisk of dimension 2 or more is of this form. There exist n univariate Blaschke products such that f of z1 dot 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 zn is the Blaschke product b1 acting on some one of these variables, comma, the Blaschke product D2, that depends on another one of these variables, and so on. Okay, so you see there is, as you can see, a certain rigidity in the structure of a proper holomorphic map from the unit polydisk to itself. But be that as it may, this example does not exhibit an analog of Cartan's theorem, because please note, remember the definition of a Blaschke product, this capital F is still in general a many-to-one map. Okay, so please keep that thought in mind. Okay, so now I want to move closer towards that statement, that vague statement I had in my first slide, which I had labeled as a phenomenon. Okay, so that result about balls, two-dimensional round balls, was an illustration of that phenomenon. So that assertion, it arises from a certain heuristic. So by a heuristic, I mean a collection of, on the face of it, somewhat imprecise principles, which can be made precise and which lead to proofs of the phenomenon that I want to talk about. And to do that, for the purposes of this talk, I want to, at least for the purposes of about one half of this talk, I want to put up certain blanket hypotheses. Okay, for the next, I don't know, for the next 20 odd minutes, I'm going to be within the ambit of these blanket hypotheses. So what are they? First of all, I'm going to say that D1 is equal to D2. Now, if you cast your mind back at the phenomenon, because I haven't defined what I mean by a biholomorphism, I did not make the comment which I should have made, but alert people would have noticed, that in fact, when I say that a proper holomorphic map from D1 to D2 automatically turns out to be a biholomorphism, what this is also saying that if I have a D1 and a D2 in complex Euclidean space of the same dimension, whenever this phenomenon holds true, and whenever there is a proper holomorphic map from D1 to D2, it actually is the case that D1 and D2 are biholomorphs. Okay? So for the purposes of discussing heuristics, for the phenomenon that this talk focuses on, I actually don't lose anything in assuming D1 is equal to D2. Although I will have more to say about this going forward, and I'm making this blanket assumption largely to avoid burning up your time and my time in talking about inessential technicalities going forward. All right. So this is the first blanket assumption. The second assumption I'm going to make is that the boundary of, so I've assumed that D1 and D2 are one and the same domain. Let's call it D. The next blanket assumption is that this boundary is a C infinity smooth manifold. Okay. Now, I kind of need some condition on the boundary, right? Because remember, what the Remmerstein theorem shows is that the Cartan phenomenon will not arise when I'm looking at product domains in general, right? But then remember, product domains do not have smooth boundary. There's also a deeper reason. When the boundary of D is just C1 smooth, one actually has counterexamples, and their existence is on par with theorems in standard real differential topology that people in the audience might be familiar with, theorems about manifolds with boundary that fail in the real C1 smooth category. Okay, so counterexamples to the phenomenon that we are talking about, their existence is on par with other pathologies that you see in the real world with C1 smooth boundary. Okay, so you might want to ask, all right, there's this wide gulf between C1 smooth boundary and C infinity. All right, well, there is a story which is, of course, particularly engaging to analysts. But since I'm addressing a wider audience, I'll pass over that question. Okay, so sorry, pass. This is an important hypothesis. This is my third blanket hypothesis. D is Levy pseudoconvex. And on this, I'll have to talk a little bit. What do I mean? So first, let's talk about generalities to motivate this concept in general, and then look at a definition that's easy to comprehend under our other blanket assumptions, which is domains with smooth boundary. Okay. All right. So loosely speaking, suppose I have a domain with a smooth boundary. The purport of D not being pseudoconvex is that there is a strictly larger domain, which I call omega, that contains D, so that every single function that is holomorphic on D, in fact, extends to a holomorphic function on the larger domain. So this is very much, so if you look at what not being pseudoconvex means, you'll quickly realize that any planar domain is not pseudoconvex. In other words, any planar domain is pseudoconvex. So this, what I just said by means of motivation, is very much a higher dimensional phenomenon, and it's kind of staggering. This is what's kind of scary about complex analysis in more than one variable, that there exist any number of examples of domains with the property that every single function on such a domain simultaneously extends to a fixed, strictly larger domain. And so you see, if that were to happen, then the locus of the phenomenon that we are interested in, it would shift to the bigger domain, right? Why would I, if I am talking about the behavior of holomorphic functions and holomorphic maps, why would I talk about D, right? So that is why I want to stipulate that this thing cannot happen. All right. Now let's give an actual definition. What I stated above is a definition, but only in the smoothly bounded case. However, I can give you a rigorous definition in the case that D has C2 smooth boundary. And the definition is as follows. Choose a slightly larger open set that contains D closure and fix a defining function rho for this domain. We say that D is Levy pseudoconvex. This is the term I'm defining. If you notice there's this particular quadratic form that I have just defined. This quadratic form that I just defined is non-negative at every boundary point on a very specific subspace of the real tangent space to the boundary manifold. And that subspace is this intersection. So you see, what I've done is I want this quadratic form to be non-negative on only those vectors that lie in this intersection. But see how this intersection is constructed. This is precisely the maximal complex subspace sitting inside the real tangent space at the boundary point P to the manifold boundary of D. Okay. All right, fine, great. I've just given you the definition, but what is its meaning? This is what the definition means. It to say that D is Levy pseudoconvex is to say that number one, D is C2 smoothly bounded and enjoys a weak form of convexity, which is preserved by the isomorphisms of the category we are discussing. Or in more pedestrian words, Levy pseudoconvexity is a weak form of convexity, sufficiently weak that it is preserved under biholomorphisms. Now, why is that so? Well, if you look at this, do you see, but for the fact that I am applying these mixed Cauchy-Riemann derivatives to rho, I actually have something that reminds you of the Hessian, except that this is not the Hessian. So now let's think. If I have a C2 smooth convex function, and I want to say that the region, what do I mean by saying that a C2 smooth function is convex? What I mean is that the region above the graph of this function sitting in Rn is a convex set. Then in the C2 case, convexity is characterized by having the real Hessian with respect to the n-1 variables of this function being positive definite. Remember, this is something we learn in calculus. Now, if I have a C2 smoothly bounded real convex body, then what I just said translates to saying that the real Hessian of the defining form, of the defining function for this convex body is positive semi-definite, not on the full vector space, but on the tangent space to the boundary at each point. So that's convexity. Now, this property is preserved by all affine maps, but in general, convexity is not preserved by nonlinear maps. So this, instead of the familiar Hessian, I'm looking at the complex Hessian, and this is a property that is weaker than convexity, but happens to be preserved by holomorphisms. So having said all of this, it would be unnatural for a convex domain to not be Levy pseudoconvex, right? So any convex domain is pseudoconvex. I haven't really defined pseudoconvexity. I've just loosely talked about what it means. But any convex domain in CN is Levy pseudoconvex. So in a sense, I haven't lied to you to say that you should understand Levy pseudoconvexity as a weak form of convexity. So this is my third blanket assumption, okay? All right. Now, let me define for you a heuristic which, whenever we can make it work, is going to result in a hard theorem with a hard proof that establishes that given a smoothly bounded domain in CN, please note n greater than or equal to 2, any proper holomorphic map actually turns out to be a biholomorphism, okay? So this is the heuristic, okay? So what I'm going to talk about is a set of steps which, whenever you can justify them, will result in the proof of a theorem. Step 1. All right, so remember D1 is equal to D2, so consider a proper holomorphic self-map. Step 1 is to show that F extends to a C infinity smooth map. I'm going to call that F tilde from the closure of D2 itself. And then remember the definition of properness, that's going to force the boundary to map to the boundary, okay? Now, by the way, I do want to point out that this is a hard first step. I mean, come on. This is really, I'm demanding something really significant, right? Because in general, why would you even expect such a map to extend even continuously to the boundary? But I am in fact saying, let step 1 be to show smooth extension. But paradoxically, while the circumstances in which one can prove step 1 seem very challenging, there are numerous approaches and numerous results in this area The first, I've got to mention this, the first result of this kind was for D being strictly pseudoconvex. I haven't defined what I mean by strictly pseudoconvex. I'll come back and give you the definition so as not to interrupt the flow of thought. The first instance of step one was this really famous result by Charles Pfefferman, which essentially triggered off an absolute frenzy in establishing results of this kind. C infinity smooth extension to the boundary of proper holomorphic maps. Okay, so there are numerous ways in which I can carry out step one. As for that result for the ball in C2, Cartan had used a two-variable analog of the Schwarz reflection principle. Step two. So this is not something that you need to prove. Well, I mean, what I'm about to say requires a proof, but this is really soft. This is an easy statement. Assume that F is branched, by which I mean that the complex Jacobian of this F vanishes somewhere. That's precisely what I said. I'm going to call that set of all points where the complex Jacobian vanishes. I'm going to call that E sub F. Assume that the set is non-empty. Then it turns out that for dimension 2 and higher, this set is going to be non-compact. And when one looks at the closure of this set in the ambient Cn, then all the limit points that E sub F picks up that are not already in E sub F lie in the boundary. I see someone raised their hand. I had a hand raised. Sohinipal, do you have a question? Is that a question? No? Okay. So let's move on. So step two says that when I look at the set where F is branched, and I look at its closure in the ambient Cn, then all of the limit points that E sub F has that are not already in E sub F are actually boundary points. Now, this absolutely is not the case in one dimension. This is very much a higher dimensional phenomenon. Okay, so in fact, step two, you could say that what is implicated in the results, like Cartan's theorem, is what step two is telling you. Okay, all right. Now here's a simple observation. I need that to make sense of the next step, which is that properness is a good behavior constraint, so that if I look at if rho is a defining function for D, then the function rho composed with F is also a defining function. Okay, it remains a defining function. So this is some type of a Hopf lemma. All right. So this is not hard. The meat of what I want to say is now the next step in my heuristic. Okay. So I stated as step one, proving instances of the phenomenon that I stated in the very first slide. One way of proving theorems of this kind is to first establish step one. Step two is a general statement. Okay. Now let's look at step three. Step three, you fix a point on the boundary of D. Remember, now D is a manifold, is a smooth manifold. So remember, those of you who have a Bailey introduction to differential geometry will know, if I ask you, as a thing, what is a tangent vector to a manifold? You would say that as a thing, a tangent vector is a partial differential operator, or is a derivation, right? This is what you learn in probably the very first chapter of the first course in differential topology. Now, I want to talk about what I mean by a first order complex tangential differential operator? Well, it's something like a tangent vector, except that I want these vectors to point in. Remember this object we have seen when defining Levy pseudoconvexity. I want this vector to point in along the maximal complex subspace of the tangent space. So complex tangential differential operator is a smooth, non-vanishing local section, not of the tangent bundle, but this bundle, okay? So I define this number, tau of p. This is defined as the infimum of all natural numbers, such that there is an mth order complex tangential differential operator. Now, what does that mean? Well, that simply means, so having defined for you a first order complex tangential differential operator, an mth order complex tangential differential operator is simply an m-fold composition of these guys that I just defined. So at the point, boundary point P, tau sub P is the infimum over all m such that there is an mth order complex tangential differential operator that does not annihilate the Levy determinant at the point P. All right, what does that mean? So I need to explain what I mean by the Levy determinant. So this is an excuse to introduce a word, a term, a piece of jargon. So remember this quadratic form. This quadratic form, when restricted to this specific subspace of the ambient space, having restricted this quadratic form, the form that I get is called the Levy form, right? Now, Levy pseudoconvexity. So now please check that the restricted form itself is a Hermitian form, and the Levy determinant is simply the determinant not of the complex Hessian, but of the Levy form. That's what I mean by the Levy determinant. All right, now I'm going to talk about, I've talked about tau of P. Remember, a proper holomorphic map in my heuristic, in step one, I've already acknowledged that I can somehow or the other, by hook or by crook, extend my proper holomorphic map to the boundary. So f tilde of P makes sense. So I can just apply this definition to the point, boundary point, f tilde of P. And owing to step two, okay, the fact that, what is step two? I should go back. Step two is that limit points not already in the branch locus are going to sit inside the boundary. It will follow that tau of P always dominates tau of f tilde of P. This is not a hard statement. The hard statement is that whenever P is a limit point of the branching locus, then tau of P is strictly greater than tau of f tilde of P. So again, step three, I want to point out, step three is a general phenomenon. Step three, like step two, is a general phenomenon. Where one needs to prove something is step four of my heuristic. So step two and step three basically collude to make possible what I'm saying step four constitutes. What you now do is you look at what happens when I replace f by its iterates. Okay, what the hell does that statement mean? I just said, observe what happens. Well, the thing is, to prove a theorem that illustrates again, let's remind ourselves, I had this phenomenon that I posted on slide 1. So to prove a theorem that illustrates a phenomenon, what I actually want out of step 4 is that as m goes to infinity, this statement, which I have highlighted by a star, is going to be contradicted. All right? Okay. So step 4 is a step where you actually have to do something. You now need to impose reasonable conditions on the domain. So this is where geometry comes into the picture, such that as m goes to infinity, somehow or the other, the statement is going to be contradicted. Okay. So what does that mean? For the statement to be contradicted, for a contradiction to arise at all, I am assuming that the substance of the statement holds true, which means that my map is branched. So a contradiction will reveal that f is unbranched, which will not really deliver the result that you want. It will simply have proved. So remember, this is the complex. So to say that f is unbranched means to say that E sub f is empty, which means by the complex analog of the inverse function theorem, all you would have proven is that f is locally invertible. This is not quite the result that we want, right? Because the phenomenon is that if f is a proper holomorphic map, then f should be invertible. But the blanket hypotheses that I took some time to describe are actually enough, it turns out, are enough to establish that, in fact, if you have that contradiction in step 4, which means that f is unbranched, then f is invertible. Now, in the case of B2, this is actually not very hard to show. One actually applies a monodromy theorem to the germ of the local holomorphic inverses of f. Because f is unbranched, f will have at each point a local holomorphic inverse, and one just applies a monodromy principle. Things are not so easy in greater generality, and in these days, for this particular heuristic that I outlined, what one does is one applies Pinchuk's theorem. So what is Pinchuk's theorem? You know, I really wish I could have talked about this theorem. It's really lovely, but I found that I would not have enough time to do so, so I'm just going to leave it at that, okay? So there is some sort of a monodromy principle. In the case of the ball in 2 dimensions, you just do this by bare hands. Where you cannot do it by bare hands, you use a general principle, which is Pinchuk's theorem, which would involve some amount of algebraic topology. Okay, so sorry about that. We just wouldn't have the time to get into the weeds of that result. Okay, so I outlined a heuristic. Some work needs to be done to execute step 1. Step 2 and step 3 are given. Step 2 and step 3 are simply statements that are given which allow us to make sense of step 4, which is again where hard work is involved. Okay. All right. So given this heuristic, let's look at some results. Okay. Again, let's remind ourselves that the blanket hypotheses 1 through 3 are in effect. And I am now, instead of going on saying that phenomenon in slide 1, I'm going to give a name to this phenomenon. I'm going to call it the rigidity phenomenon. And to disambiguate from similar phenomena which involve not good behavior of the map F, but maybe its action on homology or cohomology or whatever. When I need to disambiguate, I'm going to call it geometric rigidity. Okay. So the first result. So remember, Cartan, that is Henri Cartan, had proved had established this phenomenon, the rigidity phenomenon for the ball in 2 dimensions. It is Herb Alexander who established geometric rigidity for the round ball in any Cn n greater than or equal to 2. Now, Burns and Schneider generalized the above result to the case of strictly pseudoconvex domains. So what do I mean by strict pseudoconvexity? What I mean by strict pseudoconvexity is that the Levy form is not just positive semi-definite, but strictly positive definite at each boundary point. Okay, so let's remind ourselves. The Levy form is a certain quadratic form. Levy pseudoconvexity means the positive semi-definiteness of this form when restricted to this subspace of the ambient tangent space. So strict Levy pseudoconvexity means that the Levy form is not just positive semi-definite, but is strictly positive definite. So now you see it's kind of easy to see why the Burns-Schneider result would be true by appealing to our heuristic. Because I have already told you that when D is strictly pseudoconvex, there's this really landmark result by Pfefferman which establishes step 1. But now let's look at star. Star, well, let's look at the definition of tau sub p. You see our Levy determinant right on the nose by strict pseudoconvexity, right on the nose, our Levy determinant is non-vanishing. So this tau sub p is going to be 0. So if my map were branched, then I would get a contradiction to the strict inequality, because neither side can be anything but 0. Yes, and yet if my map were branched, I should have this strict inequality. Get that? That is the contradiction. And so for really basic reasons, following my heuristic, this is Burns-Schneider result, done. Now, Bedford and Bell prove this without the strict pseudoconvexity hypothesis, but things get really hairy at this point because the rank of the Levy form could change from point to point on the boundary. That's really the explanation of the difficulty. And so the way to finesse the difficulty is by assuming that the boundary of D is not just a smooth manifold, but a real analytic manifold. Okay. I do want to clarify, by the way, that I am not saying that each of these 3 results strictly follows the heuristic that I outlined. These proofs may be a little, may diverge in their specifics from the heuristic that I outlined. But what I want to say is that one can reprove all of these 3 results following the heuristic that I outlined. Okay, so now let's prove something. You know, they keep saying that a talk should have at least 1 proof. So given the data that you have in this slide, we should be able to prove we will be able to prove the inequivalence of the ball, the round ball in Cn, and the unit polydisk in Cn when n is greater than or equal to 2. And this is how the proof goes. So please note that the set of all proper holomorphic self-maps, either for the ball or for the unit polydisk, they are semigroups with respect to composition. So you see, if there were a biholomorphism between these 2 guys, then this biholomorphism would introduce an isomorphism of semigroups. And I can actually write down this isomorphism by hand. If there were a biholomorphism phi, then this mapping theta that carries a proper holomorphic map, proper holomorphic self-map of the ball to a proper holomorphic self-map of the unit polydisk would simply be given by conjugacy. Okay. But you see, these 2 semigroups, So if there were a biholomorphism, this conjugacy would give me a semigroup isomorphism, but these semigroups are non-isomorphic because remember, we computed the semigroup of proper holomorphic self-maps of the unit polydisk. And in general, this semigroup has a lot of maps that are non-invertible, whereas the semigroup of proper holomorphic maps of the ball by Alexander's theorem, in fact, has the structure of the group. So they cannot be isomorphic, hence a contradiction. By the way, in its guts, Cartan's proof really had the same idea. One needs to prove that two algebraic objects are non-isomorphic. But Cartan's proof actually involved a by-hand calculation of the group of automorphisms of V2 and the group of automorphisms of the unit bidisk. So he actually performed a computation and had an actual computation of these two semigroups, and they proved to be non-isomorphic. So that was Cartan's proof. Okay. Let me actually skip this slide because I'm not doing so well on time. Okay. I want to actually talk about some other contexts, partly because the advisors, the organizers told me to have a talk which embraces both geometry and analysis. Now, unfortunately, I'm not a geometer, although you cannot actually do away with some amount of analysis, even when looking at the rigidity phenomenon, where the manifolds are simply domains in Euclidean space. But in fact, if I go to a different realm, if I actually look at abstract complex manifolds, if I'm not looking at domains in CM, if I'm looking at a more general universe, then I want to point out that in the setting of complex manifolds, this geometric rigidity was established well ahead of their non-compact counterparts. And let's just look at a couple of examples. I choose to mention these examples simply because these happen to be geometry results that I, as an analyst, happen to understand and have used in my work. So this is a result by Kobayashi and Ochiai. So our protagonists are compact complex manifolds of the same dimension, where the compact manifold Y is of general type. So I'm not going to get into a definition of what general type means, but X and for those who in the audience who understand, X and Y, for Y to be of general type, Y is a projective manifold. And the adjective general type is meant to indicate a generic projective manifold in some very specific sense. So Y is a generic projective manifold. Now, please note that since X and Y are compact manifolds, in fact, any continuous map between them would automatically be proper. So I don't need to actually say proper. But the Kobayashi-Ochiai theorem, or at least a baby version of it, says that there are only finitely many surjective holomorphic maps from X to Y. Okay. This doesn't look like a rigidity phenomenon, but bear with me for a moment. As a corollary, we have this result. Let X be a compact complex manifold of general type, and let X and let F be a surjective holomorphic self-map of X. Then any generic point in X has exactly one pre-image out of F. Proof is really easy if you are willing to take the Kobayashi-Ochiai theorem on faith, and it goes as follows. So please note I'm in the complex category. So these are all oriented manifolds. So the topological degree of F is in fact the generic cardinality of pre-images of points. Okay. So suppose the topological degree is strictly greater than 1. Now, the topological degree is multiplicative. So if the topological degree were 1, then by multiplicativity of the topological degree, every iterate would have as topological degree the nth power of this guy. So this collection would be infinite, which contradicts the Kobayashi-Ochiai theorem, okay? Hence the proof. But you see, there is another reason why I have flashed this slide, apart from stating, so this corollary is an illustration of the rigidity phenomenon. But the other reason I had for flashing this slide is that, in fact, the heuristics for proving these sorts of results can be reverse engineered to prove results in the category of domains. The results that I have in mind are results where the conclusions are similar to this corollary. X needn't be of general type, need not necessarily be of general type, but to mitigate this problem, one assumes the action of a large Lie group acting on X. So some of you in the audience would be familiar with a result of this sort, which is the result by Paranjpe and Srinivas from the late 80s. Okay, but the point I want to make is that for those of you who do know the proofs of these results on this particular slide, there are certain heuristics I can steal from this universe. Okay, and well, what is the universe that I now want to go to? So one steal that I can perform is the use of the Schwarz lemma, because there are actually two different proofs of the Kobayashi-Ochiai theorem. Kobayashi actually gave yet another proof of the original theorem, which is from the 70s in 1991, and both proofs use versions of the Schwarz lemma. And it turns out that Schwarz lemma-based techniques, especially if you couple them with the action of a large Lie group, can be very, very versatile. And to foreshadow what I want to spend the last 10 minutes of my talk talking about is I want to get rid of the smooth boundary assumption. Okay, I want to radically get rid of that assumption. So what I just said, the versatility of Schwarz lemma-based techniques, was noted by Mock, who advocated using a form of not the Schwarz lemma as such, but a metrical version of the Schwarz lemma called the Alfors-Schwarz lemma, with the underlying metric being the Bergman metric. And one of the outcomes of this was a metric rigidity theorem by Tsai from the 90s for higher rank bounded symmetric domains. So I'm going to define what I mean by a bounded symmetric domain, but to foreshadow, I want to say that these are, in some sense, the generalization of the round ball in a very specific sense. Okay, so now, since bounded symmetric domains are homogeneous spaces, one can, from Tsai's theorem, which is a metric rigidity theorem, go to a geometric rigidity theorem. Okay, so some of my blanket hypotheses remain intact. For the rigidity phenomenon, D1 is assumed to be equal to D2, but higher rank bounded symmetry domains in no way, shape, or form have smooth boundary. Okay, but the passage from metric rigidity to geometric rigidity uses ideas. So because bounded symmetric domains are homogeneous spaces, one actually uses ideas. The proof of geometric rigidity mainly uses ideas coming from the representation theory of Lie groups. Okay, but I now want to talk about a result which has geometric rigidity for the higher rank case and the geometric rigidity of Alexander's theorem. I want to talk about a proof that in sort of a unified framework addresses both of these and more. Okay. But first I need some definitions, right? So what is a bounded symmetric domain? So a bounded domain in Cn is called a bounded symmetric domain if each point admits a symmetry. What do I mean by symmetry? I mean a holomorphic automorphism that, first of all, fixes A, but there is more. I don't merely want A to be fixed by this holomorphic automorphism, but I want A to be an isolated fixed point, and I want this automorphism to be an involution. So a bounded domain that admits a symmetry, in other words, a holomorphic automorphism with these two properties at every point A is called a bounded symmetric domain. Okay. Now, symmetry, the presence of a symmetry at each point allows us to prove that D has a large automorphism group. How large? So large that it acts transitively. Okay. All right. Okay. Now, this is a very classical result that if D is bound, because D is bounded, the automorphism group of D has the structure of a real Lie group, and in fact, D is in fact the quotient of the automorphism group of D, which is a real Lie group, by the isotropy subgroup. This is the subgroup of auto D that fixes Z. And I don't need to care what Z is because auto D acts transitively. So every isotropy subgroup is isomorphic to every other. So using this, Elie Cartan, so this is the other Cartan in our talk. This is Cartan the elder. Elie Cartan gave a complete classification, well, in the sense of mathematics, which is as a classification up to by holomorphic equivalence. So I'm not going to go through this table. I just want you to stare at this while I make a comment about rank, because I'm not going to have the time to define rank. But it turns out that bounded symmetric domains fall into 4 families and 2 individual exceptional domains, which are based on the exceptional Lie groups E6 and E7. But I'm not going to have the time to define rank, but I want you to look at this class on the first row. This is the class of P by Q matrices. All right. So you see, if I take 1 cross Q matrices and I work out what this means, that the identity, so what I do is I take Q to be equal to 1 and I take P to be some positive integer. Then let's parse what this statement means. Remember, Q is equal to 1. This, to say that 1 minus m star of m is positive, simply gives me the unit Euclidean ball. See that? So the rank of the unit Euclidean ball is the minimum of the numbers P, and remember, Q is equal to 1. So the round ball is a bounded symmetric domain of rank 1. Okay. Included in the class of bounded symmetric domains are matricial domains that satisfy this property. And those of you who work on modular forms, you might recognize these 2 families as Siegel domains. Okay. All right. So now I want to start foreshadowing the result, which I'm going to spend probably no more than 3 or 4 minutes towards the end of the talk. So let's quickly go through the slide. So I want to finish by talking about a result joint with my PhD student, Jayakrishnan Janardhanan, who is now an assistant professor at IIT Palakkad. I'm first going to talk about the mechanism of our result, and then I'm going to state our result. So our result does not use this description of the bounded symmetric domains, but uses an alternative description, which is due to Harish Chandra. The Harish Chandra realization is a realization of an n-dimensional bounded symmetric domain as the unit ball in Cn with respect to some associated complex norm. And this complex norm is called the spectral norm. So now here's the key lemma that delivers the whole the result that I'm going to come to in a moment. So this is an analytic lemma. This is really a result about the behavior of certain kinds of norms. So consider a domain D, which is the unit ball for a spectral norm. Now, for any non-zero point inside of this unit ball, delta sub D is simply the complex line generated spanned by Z. That's part of the complex line generated by Z that sits inside D. Now, here's where things get hairy, but don't worry. I'm going to conclude this talk with a picture that illustrates what this is saying. Let's suppose W1 and W2 are two regions in D, so that both of these regions contain the origin. And let's assume that F is a holomorphic self-map of D that fixes the origin. Now, if F biholomorphically maps W1 onto W2, and this second condition is sort of a condition, a bigness condition for the sets W1 and W2. There is a non-empty open set U that does not contain the U that sits inside W1 does not contain the origin, such that every complex line spanned by Z coming from this set U can be as small as you want it to be, but it has to be non-empty. Every such line sits inside W1. In other words, W1 is so large that it contains a certain pencil of complex lines. And W2 is so large that it contains this associated pencil of lines. Then F is an automorphism of D, okay? So this is a key lemma, technical, but really useful. So I just want to talk about where this lemma comes from, because it looks really, really technical, right? Now, this is a lemma due to Walter Rudin, not in this specific form, but Rudin reproved the Alexander theorem using ideas, really analytical arguments. But this is a general statement about spectral norms, and the expectation, our expectation that this lemma was going to be useful is as follows. This lemma is sort of a reverse engineered lemma that one sees in several of the results that I merely alluded to in that slide where I talked about the broader universe of geometrical results involving the action of a Lie group. So this is what I meant by there are heuristics in this other universe that we can steal from. Okay, so I have 2 more minutes. I'll probably take maybe a tiny bit more, but I do want to now, having foreshadowed the result, I want to state it. So I have 2 bounded symmetric domains of complex dimension, of the same complex dimension, but please note they are of dimension 2 or higher. Now assume so I'm not a priori assuming that D1 is equal to D2. This is the big difference, okay? Assume also that either D1 or D2 is irreducible. Then the result states that in fact D1 and D2 are actually biholomorphic to each other, and if there is any proper holomorphic So let me state that again. The conclusion of the result is that if there is any proper holomorphic mapping from D1 to D2, then in fact D1 and D2 are biholomorphic, and that proper holomorphic map is a biholomorphism. Okay, so this is a result, as I said, joint with my former student, Jay Krishnan. So the step one is actually step one of my old heuristic, except that now please note that I'm considering bounded symmetric domains. These no longer have C infinity smooth boundaries, so I can't use some jazzed up version of Pfefferman's result. But it actually turns out that when I view D1 and D2 in the Harishchandra realization, that is, they are unit norm poles, it turns out that I can extend a proper holomorphic map. In fact, I can extend a proper holomorphic map to a holomorphic map living on a slightly larger neighborhood of D1. I can do that. So that's step one. Now, step two, I'm going to be really quick about this. I'm not going to go into what the hell a Shillot boundary is, blah, blah, blah. The upshot of step two, now here is where I start diverging from my original heuristic. I can find a point, I can always find a point on some part of the boundary of D1, and I can find a sufficiently small Euclidean neighborhood of this point P, which is so small that the extension of F defined in step one, this open set is so small that it lies within the domain of the extension, but I can always find such a point where F tilde is a biholomorphism. Okay, so this is step two. Now, step three. I actually don't need the full force of D1 and D2 being bounded symmetric domains at this juncture. All I need is that aught of D1 and aught of D2 should act transitively. And what I have is an old argument by Henri Carpin, which gives us a pair of sequences. I have phi1 superscript, phi1 subscript k, and phi2 subscript k. So phi superscript 1 are maps of the form phi superscript 1 are maps that belong to aught of D1, and phi superscript 2 are maps that belong to aught of D2. And what they do is that there is such a sequence such that phi1 superscript k maps the origin into this. Remember, this open set V is really, really small and somewhere way out near the boundary, but I can map 0 into this V. And I can find a sequence of automorphisms on D2 such that I can map 0 into F of D1 intersect B. And I can find a sequence such that the sequence of phi upper 1s converges to a constant map, and the sequence of phi upper 2s converges to a constant map as well. Okay. So now now remember these W's. These W's should be reminiscent. There's a whole family of W's, and these should be reminiscent of the W's that I talked about in that key lemma. Now note what is happening. Remember, each phi upper 1k, because the sequence of phi upper 1k's converges to a constant. If I look at the inverse of these phi upper 1k's, I am blowing up this really small open set to a larger and larger set. Each of these sets contains the origin, by the way. And by passing to a subsequence, I get a sequence of W sub j's. I get a sequence of W upper k's. The subscript j pertains to the dj. I get a sequence of w's which as in the key lemma, contains the origin by construction, but by passing to a subsequence, I get bigger and bigger sets that swallow up dj. And this composition by construction is, for every k, a biholomorphism from w uppercase of 1 to w uppercase of 2. I'm still not in the situation of the key lemma because a priori my d1 is not equal to d2, but with the info that I have stated above, this info is enough to in fact infer that d1 and d2 are linearly isomorphic. So now I can kind of state that, hence, going forward, I'm just going to assume d1 is equal to d2. And the last step is an application of the key lemma to these maps f sub k. Remember, they now satisfy, because now d1 is equal to d2, they satisfy some part of the hypothesis of the key lemma, and I now need to show that everything is satisfied. So this schematic over here, you see, you are seeing a pencil of disks. This pencil of disks is meant to depict either the delta z's, where z comes from that small open set U stated in that key lemma, or it plays the role of the delta f of z's in the key lemma, okay? Now, you see, what I want is I want both W1 and W2 to contain this pencil. So now let's look at what's happening. By step 4, I have the sequence of domains that is increasing and gradually swallowing up my domain D. The issue is, you see, I could have either one of these pictures. The info I have in step 3 is not enough to infer that at some stage, some W1 upper K is going to be large enough to swallow up this pencil of disks, and the corresponding W2 is also going to swallow up the associated pencil of disks delta sub Fz. The info I have, it doesn't preclude this picture number 2, where at no finite stage is there any W1 or W2 that swallows up this pencil of analytic disks. So you see, the theorem, our theorem would follow if I had some sufficiently large K so that the left-hand picture occurs, okay? And I'm going to just finish at this point of time. I think I have taken 2-3 minutes beyond the time I was, the organizers told me to take. So I'm going to stop at this point and say that what allows picture 1 to be the picture that we obtain is the irreducibility property. Okay, so this part of the proof is fundamentally Jayakrishnan's idea. How to go from the somewhat weak information that we have in step 3 to preclude the picture number 2 and say, yes, what I have is picture number 1. All right, so at this point I stop. Thank you so much. Diganta, you are muted.
Yes, great. So I was unable to unmute myself. So you are the host, right? Or someone else is the host? Now it's fine, okay. Okay, Gautam, thanks a lot for this very nice talk. We probably have a couple, probably can take a couple of questions. I'm not very sure how it goes. If the organizers are also here.
So are the questions in the chat box?
So there are some questions in the chat box. You can write those.
Okay,
too many.
So I can't see my chat box. That's the issue I'm having. But Diganta, can you see the chat box?
Yes.
You could just read
Yes,
out the questions.
yes, I can see. Maybe I'll look at the last questions because there I can see too many.
All right.
Okay, let's go from the last one. Question in the YouTube.
Okay.
What is the idea of proof of extension of a proper holomorphic map of pseudo-convex domains to the boundary in step 1? Is pseudo-convexity used to cook fluoresubharmonic absorption functions near the boundary?
So the Pfefferman idea, who actually worked in the category of C infinity smooth strictly pseudo-convex domains, was simply a gigantic calculation where what he did was he looked at the Bergman distance rather than looking at the Euclidean distance of a strictly pseudo-convex, smoothly bounded strictly pseudo-convex domain. He looked at an intrinsic distance called the Bergman distance. And the behavior of a proper holomorphic map with respect to the Bergman distance is such that any sequence going to the boundary is a Cauchy sequence, and you can construct a completion. You can by hand, by a gigantic Riemannian geometry computation, construct a completion which gives you all the points in the completion are points in the topological boundary. So now you see, if you have a Cauchy sequence, then in the completion you'll have a limit, and so you have a candidate for the extension. For domains that are not strictly pseudo-convex, but are pseudo-convex, it's kind of hard in a few minutes to describe the method that's used, because one actually looks at techniques in PDE. One looks at fairly hard techniques of a particular partial differential equation, system of partial differential equations called the D-bar system. Okay. Now you are right that pseudo-convexity allows us to construct a fluoresubharmonic extension. But that's not the sum and substance of the method, all right?
Okay, thank you. So can we take one more question, organizers? Maybe I'll go ahead and ask.
Yes, you can take one more question.
You can take one more.
Okay,
yes.
so what is the last but one question? Okay, so if D is a symmetric domain, then D equal to odd D by quotiented by I think it's the stabilizer of a point Z, comes from transitive action, right? But why is it transitive?
Okay, yeah, continue. Yeah, go ahead.
Is odd D a bounded subgroup of PSL2R?
Well, I mean, PSL2R would actually pick out only a very specific example, right? Which therefore would be relevant to the ball. But we need to work with this definition upstairs, right? That is the basis of our understanding as to how odd D acts transitively. So the basic idea is an idea, at its heart is an idea that one is familiar with from the proof of the following statement in topology, that if you have a connected topological manifold, then the group of the automorphism group in that category, the group of self-homeomorphisms, acts transitively. It's the same idea that we use. So what we do is we look at, so you have this holomorphic isometry. So what we want to do is we want to take a point A and we pick a point B, and we want to move A to B through a finite composition of these isometries. So what happens is that the two properties of the symmetry are such that the linearization of this map has very, very specific properties, which allows us to basically see that the behavior of F sub A around A is like a reflection. So what I do is I take a small ball around a point close to A, and I apply S sub A, and this switches on a reflection which moves A to some other point. And I build a clever chain of disks, which by a concatenation of reflections moves A to some reflected image, and then I capture this reflected image of A in another ball with the property that the center of that ball moves me a little closer to the point B, and I apply another reflection, and so it goes. And the fact that S sub A behaves like a reflection comes out of looking at the linearization of this map in the tangent bundle.
Okay, thank you, Gautam. I think it's time now. Probably we should not take any more questions. Let me, let us thank, I don't know how others are going to clap. Maybe I can still clap. And let's thank the speaker.
So you have a
for this
virtual clap
talk.
option.
Oh, is there something like that?
Yes.
But I can.
Yes.
Right, you can
like
always
You
do it
can
that
also
way.
do that.
Right. Yes.